graph a quantitative variable. Remember, there's two types of variables. You have a categorical, which kind of just groups people by something that they have in common. So I always use eye color as an example. If you have brown eyes, blue eyes, green eyes, we group you with your eye color. Now, quantitative variables are going to be anything numerical. So when you walked in the door today, I asked you, how many siblings do you have? And funnily enough, a lot of us think about it really hard. And then we're like, one. And I'm like, you should know you have one sibling. But we get questions on the AP exam almost every single year asking you to describe a distribution. Now, remember, a distribution can kind of be anything. It could be a dot plot. It could be a stem plot. It could be a histogram. It can be any graphical representation of data. Now, I will say this. They will never ask you to describe a distribution in this way for categorical data. Remember, we talked about how the x-axis can kind of be put in any order that you want it to. So even if I went in and said, oh, it looks symmetric because the tallest bar is in the middle, that doesn't really matter for categorical data because you can just switch up the order because it doesn't really make a difference. Now for quantitative data, the x-axis is always going to be scaled from least to greatest. So anytime you graph something that's quantitative, it is already in numerical order. So that's why we're able to talk about these things. Now, one thing that I add to this, because every single year since I've started teaching, it's shown up on the grading rubric more prominently, is the fact that you have to include context. So when I go in and I say the average is 40 pounds, the standard deviation is 3 pounds, and there's an outlier at 65 pounds, you have no idea what I'm talking about. Yes, I described a center, I described spread, I talked about outliers, and I can even say it's unimodal and symmetric, which you guys don't really know yet. But I can say all of those things, but you don't know what I'm talking about. You don't know that I'm talking about weight of dogs until I tell you that the weight of dogs is centered at 45 pounds. It has a spread of 3 pounds. So whenever you answer questions like this, you're going to want to make sure that you include context to get full credit. They will give you credit for like, yes, you identified those things correctly, but it will never be full credit until you have that context. So let's go in. We're going to kind of talk about these 4 things separately and then talk about how you pick which one to use. You will talk about all 4 things, but you have options within them. So for the first kind of category, we have shape. The most popular and the most common one you're going to see is a unimodal distribution. So unimodal basically means it only has one peak. And with unimodal, we will eventually go on and describe a little bit further, but we'll talk about the 2 less popular ones first. First, we have bimodal. Bi means 2, so we have 2 peaks. With bimodal data, the most common questions we see are which of the following situations or variables would show bimodal data. My example every single year is if I went around the room, or we went around the room, and we plucked one hair from our head and we all measured the length of our hair, we most likely would have 2 peaks of data. We'd have a peak for everyone who has shorter hair, and we'd have a peak for everyone who has longer hair. And usually with bimodal data, you're able to kind of go in and separate it into 2 groups. I think in your practice today, you're going to talk about cereal and its sugar content. So they're going to go in and they're going to ask you, what is the sugar content of all of these cereals? And they're going to have data where you have your very healthy, less sugar cereals, and there's a peak for that. And then you're going to have data where you have like your Trix and your Fruit Loops and your Fruity Pebbles, and you have a higher peak for those. So when you go in, that would be bimodal data. And basically, we could talk about how if I was looking at cereal, I should be separating those into 2 separate categories, healthy cereal and unhealthy cereal. Now, uniform, I say that there is no clear peak A lot of the time in uniform data, the bars are going to be pretty even. There may potentially be a bar that looks taller than the others, but it's not going to be like the unimodal and bimodal where you have a gradual increase to that peak. It's going to be kind of like roughly the same. Anytime you have uniform, things like sometimes GPA can be a uniform distribution where you have like a couple of people who have this, a couple of people who have that, a couple of people on the low end. Things where it's not like there's a clear average. So usually with like test scores within the class, there's a class average. But if I look at everyone's GPA kind of in the whole school, I may see a more uniform distribution where I have people on the low end and people on the high end and kind of people in the middle. So these are the three types. Now, bimodal and uniform, you're most likely just going to identify. We never really do anything with that information. With the unimodal, that breaks down into three types of unimodal distribution. And this is the important part. You have symmetric, you have skewed left, you have skewed right. Symmetric data is basically going to be a mirror image on the left and the right-hand side. So the left-hand side looks similar to the right. I say it doesn't have to be perfect because a lot of people are like, well, this bar has a frequency of 8 and this bar has a frequency of 6. As long as it looks to be like it has reflectional symmetry. But the idea is a gradual increase to the center peak. Now for the skewedness, and this one is the most popular one. That is the one we're going to work with probably 90% of the time because that is the one we can use to calculate probabilities because it is what we will eventually call the normal distribution. You may also have heard this referred to as the bell curve, but this will have a mean and standard deviation, and this is our like golden egg in AP stats. For skewedness, the one thing that people get messed up on when it comes to skewedness is they'll look at a distribution and they'll say, okay, the data's on the right, it's skewed to the right. But when we're looking at what type of skew we have, we're looking at where is the skew? Where is the tail? Is the tail on the left-hand side or is the tail on the right-hand side? That's what tells you what type of skew you have. So in left skewed, the skewedness is on the left-hand side. In right skewed, the skewedness is on the right-hand side. So I always say, ask yourself, where is the tail? Is it on the left? Is it on the right? Don't focus on where the data is. The data is always going to be the opposite of what it's supposed to be, but you're paying attention to where does it actually taper off? Does it taper off on the low end or the high end? So that is how we determine skewed. Now, with skewed data, we can't really do a whole lot of inference because there are extreme values in that data set. So I had a student in one of my other classes who had 9 siblings, and everyone else had like 1 to 3. And so that person skewed the data because they had a lot of siblings. And so what they'll do is that will influence the mean, that will influence our spread, our standard deviation, and that changes those values. So whenever you're talking about shape, shape is going to be one of the factors that determine what you pick for center and spread. So whenever you are looking at center, the nice thing about this is it's exactly what you remember from like 3rd grade. When I find the mean, it's the same mean you've been finding since 3rd grade. Add all the numbers up, divide it by whatever you have. Median is the same thing. Put it in order, find the middle number. Now for us, we have, Riley, how many siblings do you have? 1. We're going to add Riley to our list. Kaylin, how many siblings do you have? 1. We'll add Kaylin to our list too. 1 and 1. Okay, so with the mean, typically we use mean and median. Mode is one that we're not going to necessarily talk about. I include it because it's like our worst case scenario. If you have nothing else to mention, you can talk about the mode. But mean and median are where it's at. That's what you're going to discuss. So the first thing, mean is always going to be used with symmetric data. and you can't have any outliers. Symmetric data, no outliers. So when we go in and we are trying to find a measure of center, the first thing I do is I look at the shape. If the distribution is symmetric, unimodal, symmetric, because that's kind of like if it's symmetric, it's unimodal already, you are going to find the mean of the data. Now, for us, it's the same exact mean you've seen before. Add them all up, divide by your sample size. Now, one thing that I like to point out here, sometimes on the AP exam, they're not very friendly in terms of the vocab they use. Sometimes they'll just use symbols. So if you happen to see X bar, you have to know that that represents the mean. So anytime you see X bar, that is a sample mean. Eventually we'll go in and we'll talk about population means. But for now, X bar, that represents mean. Now, I know we very easily can go in, add all these numbers up, divide it by 22, because that's how many people are in the room. However, if I had a lot of data and I needed to calculate the mean fast and I wanted to make sure it was accurate, I can use the calculator in another way. So in our calculators, we should have typed this data. Let's not forget to add in Riley and Kaylin. So I'm going to type in 2 more ones. 1, enter, 1, enter. Okay, we have our sibling data. Now, the way that I can have my calculator work for me, I can go to Stat, I can go over to Calc. So I just hit the Stat button and the right button. And the first thing you should see is 1var stats. So once you see 1var stats, go ahead and hit enter. And it's going to ask you what list do you want the calculator to look at. For the most part, you're probably just editing L1, so you don't have to change anything. If you did and you accidentally put it in L2 or L3 and you have a bunch of lists going on, you can change the list number by hitting the blue second button and whatever number you want. So if I wanted L2, I could hit second number 2. If I wanted L1 again, second number 1. The frequency list for now, we're going to leave it blank. For the most part, we don't mess with it. It's essentially if I just counted how many zeros I had, how many ones, how many twos, how many threes. But we're not going to mess with it. Let's go down to calculate. Oops. Did I type something wrong? Oh, no. Stat, calc, 1var stats. This says L1. Okay. Let's calculate. And so what you should see is a summary of that list. So a couple of things to kind of pull from this. X bar, the first thing in the list is the mean. Your calculator took all the values, added them up, divided by 22. The next important thing is going to be this SX, which we'll kind of talk about once we get to standard deviation, but that is the standard deviation value. Another nice thing that you can kind of look at is it tells you how many numbers it looked at. It looked at 22. And then it tells you what we call the 5-number summary. So it tells you a minimum, a quartile 1, a median, a quartile 3, and a max. So that will be important at the very end of today, but it gives you all of this information. So even if you don't want to go through and add them all up and make sure they're all there and divide in the main menu, sometimes it's faster to just type into the list and just go straight down and then run 1var stats. It will always give you this information. So this is usually what I will use if I have a large data set. If I have like 5 numbers, I'm probably just going to find the mean like I'm used to finding it. Add them up, divide by 5. But anything over maybe 10, I'm most likely typing it into my calculator. So our mean is 2.27 siblings. So let's write that down. We have 2.27 siblings. And I know I've mentioned before, you can't have a half of a sibling even though you think that they are not worthy. But in the case of reporting means, we will report the decimal value. The only time in actual stats, other than like what we were doing in terms of like deciding discrete continuous, that you will round a person to a whole number is if you're trying to find a sample size, because you're actually using that number to go out and collect data. Otherwise, decimals are completely fine. Okay. Now to kind of talk about why the mean is paired with symmetric data. So I have a student who took 7 exams, and it looks like for the most part they scored between an 88 and a 98. And then one day they missed the test, they never made it up, and they have this 0, which we can consider an extreme value. We will eventually be able to talk about this in terms of is it an outlier or not, but for now, we're just going to say it's extreme compared to the rest of the data. So I went in and I said, okay, if we can eliminate the outlier, there's no excuse, they didn't take the test, they never showed up, nothing worked, and they said, it's fine, we'll take the 0, we would have an average of 78.29%. which very clearly, compared to the other test scores they're making, is not very representative of how they perform in the class. So say, for instance, we go back later and we find out they were sick, they were in the hospital, something happened, something extreme that made it so that that test didn't have to count. So if that happens and we eliminate the outlier, which is 0, and we recalculate this mean, add them all up, divide by 6 now, we would get a test average of 91.33%. So when you see that this change happens, that means that the outlier is affecting the mean. So it brought it down almost 13 points-ish, roughly. So from a 91 to a 78. So with that change, the outlier influenced that value. It brought it down. Brought the average, if I can spell today, B-R-O-U-G-H-T, brought the average down. Now, the reason why it went down and not up very clearly is that the outlier was on the lower end. So anytime you have an extreme value of data in your data set, if it's on the lower end, it's going to bring the mean down. If it's on the upper end, it's going to bring the mean up. And what we call the mean is it is a non-resistant measure. So it is easily influenced. Any number that you throw in there, it's like, wow, I want to get closer to that number, and it will go towards it. So anytime you have skewedness, anytime, bless you, you have outliers, it is going to be affected. And so in those cases, you don't want to use the mean. However, if you were to have skewed data, doesn't matter what direction and or outliers, you are going to want to use the median. Now, even if I had that 0, so I go in, they took the 0, we decided there's no reason why they shouldn't have taken the test, they just decided not to take it, and so we look at the median score instead. I put all the tests in order, like you would for finding the median, and you can still go old school, cross off on each side until you get to the middle, and we can see that if I take the median instead of the mean, I'm going to get an average of 90%, compared to if the outlier was still included, the 78.29%. So what happens is the median is a better representation when you have outliers or when you have skewedness. Now, what we need to learn from this, if the mean is less than the median, that means the average is pulled to a smaller value. And so typically we say that tells us it's skewed to the left. So if the mean is less than the median, that means the mean is smaller. So that means there's extreme values on the low end. And we'll kind of talk about the flip of that in just a second. Now, the one thing I have on here that is not something that's on the formula chart, but it's sometimes helpful, this n+1 divided by 2 basically is splitting your data in half, and it's finding where the median is. So in the cases of location, please don't make the mistake of, if I have 100 data points and I use this formula and it tells me it's supposed to be 50, 101, 1.5 or 49.5, whatever it is. That's not the median, that's just the location. So this tells you the place value of where the median would be. So it's not on the formula chart. It's not actually like required. You can definitely count where the median ends up, but this is helpful for questions where you have a histogram and they want you to find the median within a histogram. If I know what number it should be, since everything is least to greatest, I can just count until I get to that number. So median is what we use with skewed data or outliers. Now mode, I'm not going to spend a ton of time talking about. It is the number that occurs the most. However, I do refer to it as kind of our worst case scenario. If you just for some reason, and by the time you get to the AP exam, there should be no reason because we'll talk about this plenty, you completely blank and you're like, all I remember is mode. Mode is the number that occurs the most. So the most occurring value in a data set. If that's all you can talk about, mention it because something is better than nothing. Now, referring back to the mean is less than the median, so I know it's skewed to the left. There is a relationship that kind of carries over in each of these distributions. So I have all three. I have unimodal and symmetric. I have unimodal and left skewed and unimodal and right skewed. If the data is symmetric, all of these values should be approximately the same. They should all have roughly the same mean, median, and mode. Now, I always get the question, how alike do they have to be? Well, if my data is from 1 to 5,000 and my mean is 450 and my median is 455 or 460, I'm going to say that those are pretty close to each other considering the range of my values, 1 to 5,000. If my data is 1 to 10 and my median is 5 and my mean is 6 or 7, that's a huge difference in comparison to the scale. So when I have such a small scale, I'm expecting like decimals of a difference, not entire whole number values. So pay attention to the scale, and it is kind of a judgment call in the end of, are these close enough, are they not? But if you have a really big scale and it's like 2 or 3 numbers apart, it's probably fine. And we're going to say it's still symmetric. Now for the others, here's where I kind of pull in my real world examples. If I'm taking the class average and I have a student who gets a 0 on a quiz, 0 on a quiz, and I'm like, okay, I'm going to take the class average. I'm going to see what everybody got. That 0 is going to bring the mean down. So the mean is actually going to decrease because that 0 was affecting it, which is why the mean is less than the median. Now the mode ends up being bigger just with the nature of a skewed distribution, but the mean and median relationship is what is most important. Now on the other end, I always say if I am looking at salaries and I have a CEO who makes 10 million a year, 10 million a year, and they want to hire people at their company, everybody else making like 75,000 a year, 100,000 maybe. And so they're like, okay, well, let's factor in the CEO's salary into this average, and it's going to look like everyone else is getting paid more. So they put the 10 million in, and it starts to look like everyone's getting paid like 250, 300,000 versus what the actual true value is. So that CEO, that extreme value on the upper end, actually makes the mean bigger than the median. So anytime you have extreme values, look at where they're located, and that's going to describe the shape and the relationship between the mean and median. And this is why we use the median for skewed data. It's not going to be influenced. It's going to stay true to that center no matter what. Okay, center. You're picking mean or median. Mean, symmetric data, median, skewed or outliers. Kind of summary there. Once you've made that decision, everything else kind of falls in place. So once you've decided, am I using the mean or the median, you will go in and talk about spread. So spread is what we kind of refer to as the variability of the data, meaning like how many different numbers do I have? How spread out are they? Are they close together? Are they far apart? And one of the ways you've talked about spread before in other classes is with range. So that's the max number minus the min number gives you the range. Generally, for the most part, I will kind of throw this in there as a piece of information when I'm describing a distribution. However, it's not the only thing I would mention. It's still what you remember, again, from 3rd grade when you learned mean, median, mode, but it doesn't tell us a whole lot. If I have my test scores and someone made 100 and someone made a 0, and I tell you the range of the test scores is 100, that doesn't really say a whole lot about what's going on with the class. So what we report instead are the standard deviation or the IQR. So standard deviation, a little note here. This will always pair with mean. Anytime you pick mean from symmetric, no outlier, symmetric, no outliers. Anytime you pick mean, you're picking standard deviation automatically, no questions, always together. The reason being, in order to find the standard deviation, you have to have the mean in the formula. So you'll notice X bar is in the formula for standard deviation. You have to have it. So if I have the mean, why am I not using the mean? So it's kind of like paired together forever. Now, what does the standard deviation actually represent? So it's talking about the typical deviation from the mean. So how far off is this data? So if I went in and I was looking at our sibling data, which I do have, hold on one second, let me pull it up real fast. In that 1var stats, you'll notice that we had SX. That's standard deviation. So what this number represents is if 2.27 is the center, then I can expect my data to vary, and we usually add them and subtract them. To vary, if I add 1.8 to 2.2 and I subtract 1.8 from 2.2, that's going to kind of create a range where most of my values are in. And in the grand scheme of things, once we get to normal distributions officially, you're kind of having most of your data points within 3 standard deviations. So you may kind of like from some science class remember, like we talked about standard deviations in the normal curve. That's where this is coming from. So in our notes for now, all you have to know is that a standard deviation represents how far away from the mean, deviation from the mean, your data points are. Now, in order to find this, you would technically have to go in and subtract all of the data values with the mean and get those distances. We will never, ever, ever, ever in a million years make you do this by hand. This is why I showed you 1var stats. Your calculator will do it every single time. If they don't give you data, they're giving you the number. You will not have to use this formula. It is on the formula chart. But please do not stress about looking at all of these things and wondering what the heck am I supposed to do with that. You will never use it. Guaranteed. You get your calculator the entire time on the AP exam. You get your calculator the entire time on these unit tests. So you don't have to worry about doing it by hand. This is on your formula chart, so if you look at it and are like, what the heck is that? It's there, but you will never use it. Now, one little piece of information I'm going to pull from this, just again, remember SX stands for standard deviation. The other part that I like to mention here, the inside of this square root, this is something that we refer to as the variance of a sample. And what that represents is the average squared deviation. Basically, if I take distances, some of them can be positive, some of them can be negative. So what we do is we square everything to make it all like on even playing field. And so sometimes they'll ask you, what is the variance of this data set? And all you have to do is square the standard deviation. They're not going to ask you anything too like compelling about it, but they may just ask you, what is it? And all it is the standard deviation squared. So keep that in mind. Not a huge concept, but it is within the standard deviation itself. Now, what I will have you do, because I will get questions, if you are asked to interpret the standard deviation, and you most likely will be asked to interpret a standard deviation, this is the sentence stem I would use every single time. So back to my siblings. The number of siblings in second period AP statistics varies from the mean by, what did I say, 1.8 something, 1.8 siblings. So it's literally a fill in the blank. The most important part I can tell you from this is you have to include context. If you do not have context, they are not going to give you credit. If I just say the standard deviation is 1.3, that's not interpreting. You have to tell them what this number actually represents. The other thing is making sure you include units. The units are always going to match whatever the data is. So since my data was number of siblings, my units for standard deviation is number of siblings. Now, this last part just kind of summarizes some other things about standard deviation. It's always positive because we square it. It's going to be 0 when all observations are equal. By that I mean, if by some miracle, I asked everybody who walked in the door how many siblings they had, and every single person said 2. Then our standard deviation would be 0 because there's no deviation from the mean. So if we all said 2, the average is going to be 2, meaning all of our data points have no distance between the value and the mean. So it's 0. The other thing, it's always going to have the same units. It is one of the non-resistant things. So since it's dependent on what the mean is, if the mean is getting influenced, the standard deviation is getting influenced. They're buddies. Whatever they do, they go together. So they are both non-resistant measures. Now, the last little bit that I include is a question that we see quite often, and it's one where it's a dot plot. And we always get like, which one of these has the biggest standard deviation? If you look at a graph, it could be a histogram, it could be a stem and leaf plot, and all of the data values are on the side. So like I have one cluster over here, I have one cluster over here, and they're spread out as far as they can be. That is going to have the largest standard deviation. The further your data is away from the mean, the bigger your standard deviation ends up being because they're deviating far from the mean. So I always include that because it pops up more frequently than I would think, at least like every other year. So I like to have it there. Okay, IQR, 5-number summary, and box plot all kind of go together. The first thing I'm going to mention, IQR pair with your median. So this means it's for our skewed data or data with outliers, or both. So with the IQR, it needs a couple of things. Interquartile range is what it stands for. And basically, it's going to represent the middle 50%. And I know that's not technically written anywhere, I don't think, so I'm going to write it in. Middle 50%. So what each of these things mean, quarter 1, median, quarter 3, they represent percentiles. So we've talked about percentiles already. We said like if you score in the 99th percentile on the ACT, you scored higher than 99% of people. With that, the 25th percentile is quarter 1. Because that represents 25% of your data. Technically, the median is quarter 2, but we always call it the median. That's the 50th percentile. And quarter 3 is the 75th percentile because 75% of the data is to the left. Now, what we do with this is we call this summary of data a 5-number summary. And sometimes they will present it to you so that min, Q1, median, Q3, max. They will present it almost like it's in roster notation where they'll have the curly brackets and they'll list the 5 values inside. Sometimes they give you a table and they say, here's all of these numbers, make a box plot or decide if it's symmetric or skewed. And you can kind of look at these and see if I have the mean, comparing it to the median. If I need to make a box plot, these are the numbers that I have. But this 5-number summary will always be these 5 values. And one thing to remind you of really quickly before I go and fill stuff in, we get the 5-number summary at the very, very bottom of one of our stats. So you'll notice it says min, Q1, median, Q3, max. So you don't have to find it by hand. I'm going to show you that you can, but it will always be there. Type in your data, run one var stats. So for us, we're going to kind of look at it by hand. If by some miracle, I look at the data and it's sorted for me and there's not a ton of numbers and I don't want to type them all in my calculator, so I'm just going to do it by hand, you can. So just to kind of walk through that process really quickly. If I want to find the median, I'm going to do the same thing I did above. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 3. 1, 2, 3, until I get to the middle. So in the middle, if it's a single digit, that is just the median. If it's 2, you're going to go in, you're going to take an average. In our case, that number is 7 because they're both 7. And what the median is kind of doing is it's splitting your data in half. So if you had a single value, it would kind of just be like eliminated in a sense. But since we have 2, it's basically taking our data, splitting it into a lower half and an upper half. And so what we do with that is we find the median of the lower half and the median of the upper half. Those are our quartiles. So I'm going to go in 1, 2, 3, 1, 2, 3, 2, 1, 2, 6. So my quarter 1 ends up being 6. And then I do the same thing on the top. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. Quarter 3 ends up being 8. So that represents the 25th percentile, the 50th percentile, and the 75th percentile. Now, for max and min, those are exactly what you remember them to be. The minimum is 2. The maximum is 8.5. So if your data is already ordered and there's not a ton of it, you can always use this method to find the 5-number summary. If you're not sure that you're doing it correctly, I would say type it in your calculator, run one var stats. That will always be correct as long as you are typing in the values correctly. In this case, the IQR is the range of the interquartiles. So by that we mean we are taking Q3 minus Q1. Now this is where I'm going to kind of tell you most important thing that you have to know on the AP exam without a formula chart is Q3 minus Q1, because that is not on formula chart. So I kind of give you tests similar to what you would see on the AP exam. You do a multiple choice, you do an FRQ. I only give you the formulas they give you on the AP exam. So since they do not give you the interquartile range formula, I do not give you the interquartile range. So that is one you have to know. What is the interquartile for hours of sleep that AP students got? So that means I'm taking 8 minus 6, so that's going to be 2 hours. And just like standard deviation, the interquartile range will have the same units as the data that you're collecting. Okay, this interquartile range, not on the one var stats output, just a heads up. Outliers is the last thing we'll kind of talk about because we use them in order to graph our box plots. If you only have a graph and it's a histogram and you don't know the exact data values because we lose them in histograms, that is when you can visually comment on outliers. So if I see a data point and it's way out to the right and it looks like it's in the 105 to 110 range, I can say there is a potential outlier at 107, whatever. So comment on it being potentially an outlier and enter in a value. It doesn't have to be exact. So you don't know what values are in there, but pick a value that's in that range. Now, if you have the actual data, they will expect you to mathematically check for an outlier. So by that I mean, we are going to use this formula. This formula is referred to as the 1.5 IQR rule. This one is not on the formula chart. Now, I say this with like a grain of salt because they don't put it on the formula chart, but from recent years, we've noticed they've been asking the question as use the 1.5 IQR rule to check for outliers. And so they're kind of giving you like a hint as to what you're supposed to be doing because you're knowing that you have to use 1.5 times IQR. It's just you have to remember the fact that you are subtracting it from quarter one and adding it to quarter three. But they've named it in most of the questions in the last couple years. They've said use the 1.5 IQR rule. So it's like, yes, you have to memorize it, but you don't really have to like fully memorize it from what we've seen. Okay, so we have a set of data. It represents the word length for randomly selected pages in Song of Solomon, and it says to mathematically check for outliers. So what we're going to do is I went ahead to save us some time. I got the 5-number summary for this data set. It's 2, 3, 4, 7, 14. So what I did is I typed all of my data into my calculator, ran one var stats. This is what I got out. The only thing I really care about are quarter one and quarter three. So the first thing we do is we find the IQR. So that's going to be 7 minus 3, which is 4. And if this happens to be an FRQ question, you have to show all of your work. So you don't have to necessarily say 7 minus 3, but you need somewhere on your paper for it to say IQR equals 4, because they will want to see that. Now, once I do that, I'm creating boundaries. I'm going to have a lower bound. I'm going to have an upper bound. And anything that falls within this range is acceptable. So the lower is Q1 minus 1.5 times IQR. So I'm going to do 3 minus 1.5 times IQR. And the upper is Q3 plus 1.5 times IQR. So I'm going to take Q3, which is 7, plus 1.5 times IQR. And then I get two numbers. I get -3 and I get +13. So what that means is anything in this range is not an outlier. So if I get a number that falls outside of this range, we would consider it to be an outlier in the data set. So in our case, we have an outlier at 14. I included it because I didn't have one before. So we're going to say there is an outlier at 14. And since it's a word length in terms of like letters, so I'll say at 14 letters. You don't, if you were writing this out as like an actual response, you don't need the little part I have in black that says anything outside is an outlier. They will expect to see IQR. They will expect to see your calculation for the lower bound and your calculation for the upper bound. I say this because a lot of people will look and they'll see, oh, 3 minus 1.5 times 4, that's going to be negative. It's not going to have any numbers. I'm not going to actually write it down. They will still want to see it. So even though some of them don't make sense, like you'll get negatives where negatives don't work, still write it down to get that check mark to get full credit on an FRQ. So have both boundaries. Now, the last thing we're going to talk about is a box plot. So I'm going to use my data. We need the 5-number summary. I'm going to talk about 2 of them. 5-number summary. The first one, regular old box plot. The way we do this, draw a line at every single number you have in the 5-number summary. So when I go in, I'm going to draw a line at, let me get a darker color. We're going to do one at 2, 3, 4, 7, and 14. So this is a regular box plot. For the most part, they just call all box plots, but this is one where the outlier is not actually mapped out. It's just from the 5-number summary, from the minimum, from Q1, from median, Q3, and the max. One thing I always point out, your interquartile range is the box. Q1 to Q3, that is the middle 50% of your data. Now, on the other end, we have our outlier box plot. Sometimes it's called a modified box plot, but if you see that they're doing outliers, it's outliers. So we had an outlier at 14. So in most graphs that they give you, it's usually represented by like a star, a dot, a square, something that is not connected to the box plot. And you would do it on both ends if you happen to have an upper and a lower, but we don't have a lower outlier. So I'm just going to draw my lower like I would normally do. And if you have an outlier on any end, you're not going to connect the tail. You're going to go to the next highest or lowest number. So when I look at my data set, the next highest is 11. So that's going to be our connector. Now, I get the question of, well, what happens if the outlier was my highest and my quarter 3 is the box? Then you wouldn't have a tail. You don't just add in a tail if you don't have one with numerical values. One thing before we wrap this up is I want you to know each of these sections of the box plot are 25% of data. So like even though that section on the left-hand side is really, really small in comparison to the section on the right-hand side, the Q3 to max compared to the min to Q1, they still have the same number of data points in their sections. It's 25% of your data. Bless you. So don't think that because the section is longer, there's more values in it. They all have the same values inside each part. That's why it's quartiles. Now, before I completely shut this down, we're going to talk calculator because it's going to be really helpful for you today. With your calculator, you should have data. I'm going to show you how to graph your histogram and your box plot in your calculator. So we should hopefully all have the same data. So I'm going to switch over and make sure I'm hitting the right button. Okay. The way we're going to graph this. So I have all of our sibling numbers in L1. What you want